We want to evaluate a fairly simple integral, the integral from 0 to 9 over the square roots of 2 of dx over the square roots of 81 minus x squared. I need to find a substitution that will turn 81 minus x squared into a perfect square, so that then afterwards the square root is going to disappear in the denominator. So what I'm going to remind myself of is the fundamental theorem, the trigonometric identity sine squared plus cosine squared of theta. Sine squared of theta plus cosine squared of theta is equal to 1. If I am subtracting sine squared of theta, then I have the following. I can think of 1 as being 1 squared minus sine squared theta. This is turning the difference of two squares into a perfect square. Difference of two squares into a perfect square. And the difference of two squares is exactly what we have underneath the radical. So if I am now performing the following substitution, we let x be equal to 9 times the sine of theta. In order to do a perfect substitution, we need to differentiate both sides, and we are ending up with dx is equal to 9 times cosine of theta d theta. Now looking at 81 minus x squared, 81 minus x squared, what is this going to turn into with my substitution? 81 minus x squared now is going to turn into 81 minus 9 times sine theta squared, which is equal to 81 minus 81 sine squared theta. And now you also see why we had to choose 9 times sine theta, so that we end up with 81 sine squared theta, because now I can factor and I get 81 times 1 minus sine squared theta. And you hopefully notice right now that this is exactly what we were looking for, and I can now replace 1 minus sine squared theta with, you got it, cosine squared theta. So that means now I can rewrite my integral as, let's have a look, dx is going to be replaced. Dx, right here, is going to be replaced with 9 times cosine theta d theta. 9 times cosine theta d theta, all divided by the square root of 81 minus x squared is going to be 81 cosine squared theta. Now, but what about the limits? The limits I want to change as well, so that I do not have to go back and do this later. We are going to be changing the limits. We will be changing, will change the limits. You can think about this in the following way. I always like to remind myself that these are x's, but down here in my new integral with my substitutions, I want to have thetas so that the variable matches with the variable of integration. So if I'm looking at my upper limit first, we'll change the limits. My upper limit was 9 divided by the square roots of 2. This limit has not been chosen randomly, because now we are using this substitution that we have done, that x was equal to 9 times sine theta, and I'm getting 9 over the square roots of 2 is equal to 9 times sine of theta. Dividing both sides by 9, we get 1 over the square roots of 2 is sine theta. And 1 over the square roots of 2 is nothing else but the square roots of 2 over 2. And that means that the upper limit had to be which theta produces square roots of 2 over 2. That is our good old friend pi over 4. Doing the same thing with the lower limit, this was the upper limit. Let's have a look at the lower limit. 0 is equal to 9 times sine of theta. Dividing both sides by 9, we end up with 0 is equal to sine theta. And of course, that means that theta was equal to 0. So I have my new limits, pi over 4 and 0. Let's rewrite the integral and simplify the integrand. I have the integral from 0 to pi over 4 of 9 times cosine theta d theta divided by the square roots of 81 cosine squared theta, which is a perfect square. 9 cosine theta cancels out, and I'm actually just going to be left with 1 times d theta, which by the fundamental theorem of calculus now is nothing else but theta evaluated from 0 to pi over 4, which will give us pi over 4 minus 0, which of course is just pi over 4. And we are done.